as a contrast with Morse code, we can instead build what's known as a prefix-free code. So a prefix-free code is just a code where no code word is a prefix of any other. Here's the most trivial possible example for English. So a space might be 1, E might be 01, T might be 001, A might be 0001, and so forth. So if we look at our tree of characters, we'll notice that no character is ever a prefix of another. That is, whereas before, M was a prefix of G, here all of the characters are in leaves, so we never have any ambiguity. So for example, the string I8, which is I space ATE, would be 000001 for I, a 1 for space, A would be 0001, T would be 001, and finally E would be 01. Now if you get the sequence of bits, you can trivially, I hope, see that this should be decodable. That I could say, okay, I have 000001, that must be 1, or so must be I, and then I've processed that input, now I get a 1, I know that must be a space, and so forth. So because it's prefix free, we can go back from the binary version to the original version. And so if Morse code were prefix free, we would have no need for pauses. You could tap out as fast as you wanted, and if the listener was good enough, they would be able to decode it with no pauses. Another example of a prefix-free code is just a different one. It doesn't have to look like this. It could be something like what we see here. So again, characters are always leaves because we don't want any character to be a prefix of any other. But here things are balanced out a little more nicely. So space, for example, is 111. The letter A is 1011, and so forth. So in this code, I8 would be 1000 for the I, 111 for the space, 1011 for the A, and so forth, as we just saw. And likewise, we can uniquely decode these strings because it is prefix free. So I have 1000, okay, I follow this. It's maybe feeling a little dull here. That's the letter I, and so forth. And so you can see that you can actually go backwards here without ambiguity. Now here's the interesting thing. Some prefix-free codes are better for some texts than others. So let's consider this prefix-free code on the left. The string EEEEAT is only a total of 15 bits for this left prefix-free code, the first one we saw. Whereas on the right, if we use this prefix-free code, it's EEEEAT again, but now E costs 3 bits for each E, 4 bits for the A, and 4 for the T, for a total of 20 bits. So it's actually more efficient to use this prefix-free code for EEEEAT, whereas the word Josh, if you use these two tables, I haven't shown the whole table, but here Josh would be 48 bits, and this one would be 23 bits. And the intuition here is that for this tree, the more uncommon a character is, the longer the sequence of bits. And so relatively uncommon characters, like the letter J, take tons of bits, 25 bits for just one measly J. So an observation then is that it sure would be really nice if we had a procedure that could calculate the best code for a given text, because here we can see that it depends which code we use. And so maybe if we pick the right code for each text, maybe Morse code for one text, this code for another, and this code for yet another, who knows? Maybe that would be a better way to go. Though Morse code probably not a good way to go because we want to avoid prefixes. Okay? So we'll think about this a little more, but I'll make sure this sinks in before we continue, that some prefix-free codes are better for some texts than others.